classroom at one time.
All right, sorry for the delay, folks. I had a whale of a time trying to get stuff to open. I think IDEA is open up here, but I can't see it on the toolbar right now. So who knows what there it is. Now that's here on the toolbar. Who knows what's going to go on? This could be a very short class because my tools could fail me, but we'll see what happens. This is just you never can tell. It's unpredictable. That's why you guys signed up for this course, right? It's because it's so unpredictable. You know, wanted to keep you all guessing. Yeah, that's the goal. Just as a reminder before we get started, by Wednesday of next week, I want to finalize group assignments. So please start thinking about that if you haven't already, and start coordinating with people, figure out what the groups are going to be. Again, 3 groups of 5. All right. So we're going to talk at the start of the class today. We're going to talk about sampling. By the way, I'm doing this on the Truman remote desktop, which is why it's causing so much fits. Normally this doesn't happen in this class, but there's going to be unexpected things around every turn. So let's go and talk very briefly about sampling at a very high level. And then I want to talk about some things that you should know from perspective in this course. And then I want to kind of wrap up an idea. If you've got IDEA open, great. If you don't have it open, that's fine too. It's not going to be required that you run along with it. The IDEA stuff is mostly for clarification purposes. What I recommend is that you actually have the slides and information in front of you. Also on week 7 on the Brightspace page, you'll notice that underneath the slides for today, there's a document called attribute sampling tables. You may want to have that available, as we're going to talk a little bit about what's contained within that as well. And in that note, I'm also going to open a file on my Y drive. It's going to be very helpful for me. So forgot all about that. Let's see, it's 25 or 27, 28. Yeah, okay. But let's talk at a basic level. Hopefully that Excel file will not open up in the middle of my presentation about what it is that I want you to know with respect to sampling. And I'm going to throw a disclaimer out here. I don't necessarily think that this is a high priority topic. If I ask you a question about it, it'll be one question on the exam. Most accounting firms, they use non-statistical sampling techniques. And many of our new data technologies are rendering sampling techniques obsolete. We've got a lot of new data analytics tools, even old data analytics tools that allow us to do full unit sampling instead of full unit testing instead of sampling. But that being said, this is something that's tested on the CPA exam, and it does have a basis in a lot of the work we do in auditing. So we do need to talk a little bit about the theory behind it. I am not an expert in this field, and if you say, well, I appreciate that Dr. Barnes gave us statistical prowess on this. My statistical prowess is like infinitesimal, okay? I knew enough statistics to get me through a PhD program, and that's about it. And even that's a stretch. I think I managed to fake a lot of my knowledge in that regard. So I'm not going to say that I'm a statistician and I have great mastery of this. I know enough to be dangerous, and so I'm going to teach you all enough to be dangerous. You may know more than I do, and some of this may be review, and some of this may be applicable. But let's talk a little bit about something we've talked about already in this course, and that's the idea of reasonable assurance. So why do we use sampling? The idea is that we want to actually test some of the information and not all of it. And that goes back to this idea of we can't actually accomplish reasonable assurance. It's just not something that's practical for us to achieve. Reasonable assurance, or absolute assurance. If I said reasonable assurance, I meant absolute assurance. That would involve testing everything. Now, we do have tools that allow us to test more than we used to in the past. That being said, think about a company like Amazon that literally has millions of transactions a day. It would be just absolutely impossible to test every single one of those transactions, even at a basic level. So we're going to rely on some statistical techniques, specifically sampling, to actually allow us to perform testing that gives us a good idea of what's happening, but not necessarily test everything all at once. That being said, we're going to encounter this thing called sampling risk, which we're going to call, which is going to be correlated to our risk of incorrect acceptance with respect to audit risk. And that's going to be the possibility that the sample is not drawn as representative of the population. So the auditor can reach an incorrect conclusion about the account balance of transactions based on the sample. Now, when we talked about audit risk, we specifically said that audit risk is a type 2 error, that we say there's no problem when in fact there is a problem. We can run into both types of errors when we talk about sampling risk. We could say that the sample represents that there is a problem when the population says that there's no problem, or there's no problem in the population, and vice versa. We could say that there's a problem in the sample, or there's no problem in the sample when in fact there is a problem in the population. That very closely correlates with the type of risk we're already familiar with, so it should be a fairly basic concept for us to understand. But we do need to rely on sampling to some degree because, again, it's just not feasible or practical for us to perform full testing of most of the populations that we're going to look at, or many of the populations we're going to look at. So some standard sampling assumptions that you're probably familiar with. There's the normal distribution, which is just basically this U-shaped curve. When you hear me talk about grade distribution and I'm looking for something like this, that's kind of what we're looking for, is that we want to make sure that most of our observations occur right around the mean of the population. The samples are unbiased and random. Samples are also representative of the population, and the variance of the sample is also representative of the population. And you probably know the terms for variance, standard deviation, if you remember from your statistics classes. That just basically says how far from the mean does the entire population of observations rate, and how does that distribution look when we map it out like this? This is kind of the perfect distribution. This is our normal distribution, that reverse bell-shaped curve. That's what we would, or I guess the bell-shaped curve, inverse bell-shaped curve would be weird. That'd be like that. That's a different distribution. That's a bad distribution. So a bell-shaped curve is good. Inverse bell-shaped curve is bad. So this is kind of what we're looking for, and this is what we assume in most of our situations. As far as what we're going to be talking about today, we're going to be focusing on attribute sampling. And attribute sampling is when we test for a specific characteristic of an item. Effectively, we're just answering a yes/no question or saying characteristic exists does not exist. And you may notice down here it says test of controls usually use attribute sampling, which makes sense because in test of controls, we're trying to answer a yes/no question. Is the control effective? The answer is the control is effective, then we say yes. If it's not, then we say no, which is kind of the attribute that we're testing for. Now, variable sampling, we're not going to cover in as much detail because it's a lot more complex and there's a lot more nuance to it than I'm personally comfortable with. But this is where we extrapolate dollar value differences in a sample to the population. This could be monetary unit sampling, classical variance sampling, etc. We're generally going to be involved in a test of account balances. So this would be an example where we talk about confirmations a little bit later. We talk about confirmations being used in sampling. We would actually look and see what the results of our confirmations testing are. We determine what was the misstatement in our sample, and then we would project that sample in the misstatement in the sample to the population as a whole. So if my misstatement of the sample is $1,000, that means that I believe that my population is going to be misstated by $10,000 or something along those lines. That would be an example of this type of variable sampling that we're discussing. As far as some concepts that we need to be aware of with respect to this detail, we need to talk a little bit about confidence level. Confidence level is our confidence that the sample is representative of the population. If we have larger confidence levels, those require larger samples, right? Now, remember I talked a little bit about sampling risk earlier, okay? I said sampling risk is the risk that the sample is not representative of the population. These two have an inverse relationship to one another. Specifically, if you take 100% and you subtract sampling risk, you get confidence level. Or if you take 100% and subtract confidence level, you get sampling risk. So if I tell you my sampling risk is 5%, that means my confidence level is 95%, all right? And the larger that confidence level gets, the larger my sample has to get. So if I want to be 90% confident, that's a smaller sample than if I want to be 95% confident or 99% confident. Additionally, with respect to attribute sampling, we're concerned about tolerable deviation rate. Okay, tolerable deviation is the rate of the sample the auditor is willing to accept. In unison with that, we're also can consider expected population deviation rate, which that's the deviation rate that the auditor expects in the population. That's also called historical defect rate. Now, these two are considered individually, but we also consider them jointly because the relationship between these two is really important with respect to sample size. In all situations that we're going to perform sample testing, we want tolerable deviation rates to be greater than expected population deviation rates. And that's a necessary characteristic. Think about why. It makes logical sense if you think about it. I can tolerate a 5% deviation, but I expect my deviation in the population to be 7%. What I expect to occur is greater than what I can tolerate, meaning that I have to test everything. I can't rely on sampling because what I expect to happen, my deviation rate is much greater than what the population is going to give me. So I want this number up here, this tolerable deviation rate, the highest rate I can tolerate, to be larger than this number right here. And the larger that difference is, the smaller my sample gets. So if I say this is 10% and this is 1%, I'm probably going to have a very small sample. If I say that this is 6% and this is 4%, my sample gets much, much larger because I need more information to get more confidence in that area. So the distance between the tolerable deviation rate and the expected population deviation rate is inversely related to its sample size. So if it's 9% distance, that's much going to be a smaller sample size than if it's going to be a 2% distance. Now, interestingly, you probably already know this because you're statistics classes, but unless the population is relatively small, less than 1,000 observations, population size is not highly correlated to sample size. So if we're testing a million, or we're testing a population of 1 million or a population of 1 billion, our sample usually is not going to change at that remote level. Usually you get about 500,000, it doesn't vary at all, okay? Which is kind of an interesting characteristic. Usually our sample is going to get for about 100 to 200 items for really large samples, but it doesn't go much beyond that. All right, here's what I'd like to do. We're going to jump away from the slides for a second because I got these slides up here, but I've actually got a spreadsheet that I want to fill out here. And one way that we're going to use to fill out the spreadsheet is that document that I put on right space for you. So it's called attribute sampling tables. And I want to explain really quick what's happening here, because we're going to use all of these tables to some degree. Again, I should have this open, and come on, you can do this. I believe in you. I believe in you. So basically what we're going to do is we're going to answer some questions. The first question we're going to answer is, what type of sample size, or what is our sample size going to be based on the attributes that we've, or the characteristics that we've looked at? Okay. So while this is opening, I'm just going to go ahead and put this in here. Oh, okay, wait a minute. Up here. Oh, it's asking me. No, I'm not going to do that. Sorry. Going to do it for Excel as well. All right. We're going to have to deal with the fact that I'm not signing in because I don't want to waste more time. So I'm not going to actually be able to plug some of these numbers in, which is kind of a problem because I want to plug the numbers in. I guess we'll just talk about what these numbers will be as we go through this because it's not going to allow me to input, I don't believe. Let's see. Yeah, it's just not responding. My apologies, guys. If I'd been a little bit more on top of things and shown up like 30 minutes before class instead of 10 minutes before class, might have been able to this. But we'll just go through and talk about what these are. So basically, what we're going to identify is we're going to identify what our sample size based on these factors, okay? So our first example says that we have a risk of incorrect acceptance of 5%, all right? Now, what does that translate to for confidence level again? So 100% minus 5%. 95%, good, okay. A tolerable deviation rate of 6%, expected population rate of 2%. So 95% confidence level, 6% tolerable deviation rate, expected population deviation rate of 2%. Let's go ahead and go to this table here. I'm going to zoom in. Got it, thank you. Quit popping up during my class. All right. So you'll notice up here that this first table that we're going to look at, it's 90%, 5% divided by confidence level. 95%, so 5% risk of incorrect acceptance. So if I start here at my tolerable deviation rate of 6% and go down to 2, you notice it's going to say 127 and 3 in parentheses. So this is telling me my sample size is 127 items. Now that 3 is relevant, but we'll talk about what that 3 means here in just a little bit, okay? Is it important? Yes, but it's not important yet, okay? So we'll just keep a note of that. Let's do another one real quick. I'm not going to do all of these, but let's go ahead and do number 3. So number 3 says risk of incorrect acceptance of 10%, meaning our confidence level has to be 90%. Good, 90%. Tolerable deviation rate of 4%, expected population deviation rate of 1%. So we're going to go back to our tables, and this time we can't use the 95% confidence level table because we need to use a different one. So we're going to go to the 90% desired confidence level. So overall, will our samples be smaller or larger in this table? Smaller because we have lower confidence level. Good. All right, so we said 4% and 1%, so 96 with the parentheses of 1. So our sample is going to be 96 items, okay? 96 items. So just filling these out, if you're curious, if you want to get the answers to this, you actually will be doing a homework assignment somewhat similar to this, which we'll talk a little bit about. But this is 127, this is 88, this is 96, and this is 76, okay? So that's going to be our first part. That's using all those items. And you will notice here that these numbers are fairly consistent with one another. So we went from 127 to this one right here to 88 here. And the only thing that changed was our tolerable deviation rate. And so our tolerable deviation rate got higher. What did that do to the distance between tolerable deviation rate and expected population deviation rate? Made it larger. The larger that number gets, the smaller our sample gets. So we got a smaller sample size right here. So this is, again, this is 127, this is 88. All right. So let's go ahead and move back to the slides real quick. I need to talk about a few more concepts before we move forward. So the next step is to actually determine our sample deviation rate. All right, so this is the actual deviation rate in the sample. So we're going to perform testing once we have our sampling, and we're going to have observations of whether the control is effective or the control is a deviation. And we did that back in chapter 6. Everybody remember that? Yeah. So if it's a deviation, we note those deviations and we count those up. And then the total deviations, we divide that by our sample size to get a deviation rate. Finally, we're going to compare this. We're going to actually create a comparison, not compare this number, but we're going to create a comparison number using an upper deviation rate. Now, the upper deviation rate is just simply the sample deviation rate plus an allowance for sampling risk. Now, if you are familiar with statistics, you probably understand this concept already. If you're not, if you've forgotten kind of this concept and just don't really want to talk about statistics, well, I'm sorry, first of all, but if you don't want to remember statistics, I do want to talk really quickly about this because this is important to remember. So basically what we're saying is that we test our sample that we believe that the population deviation rate is going to be somewhere around that sample deviation rate. We don't know exactly what it is though, because we don't know what the true deviation rate of the population is. So what we do is we create a range. So if my sample deviation rate is like 3%, then I might predict that my population deviation rate is somewhere between 1% and 5%. I am concerned about that upper end, the top range, not the bottom range, because the bottom range is below the sample deviation rate. But I'm very concerned about what the highest possible deviation rate could be. So in that situation, I'm going to say I'm going to set my upper deviation rate at 5%, which is my sample deviation rate plus some sort of allocation, some sort of allowance, which we call the allowance for sampling risk added to that. So 3% plus 2% equals 5%. Now that 2%, by the way, I just made that up. That's not an actual number. It will be giving that actual number in problems if you have questions like that. And that's like a homework problem will give that to you. So that's how you determine what the upper deviation rate is. We then compare this number right here, this upper deviation rate, to the tolerable deviation rate. If our upper deviation rate, the maximum that we'd expect in the population, is less than what we can tolerate, then we accept the control as being effective. If the upper deviation rate is greater than the tolerable deviation rate, then we say the control is not effective. Okay, we say there's a problem. Now, remember those numbers in parentheses? Those numbers in parentheses are actually counts of how many deviations we can see before the control fails. That's what that number was in the first table. Now, let's go ahead and reprove that. Let's talk about what that means. And again, this is going to be a little bit difficult since I can't type in Excel, which I apologize for. Maybe I should do that. Maybe I said 152. Okay, I'm going to pause the recording and get signed in so we can actually have that typed in. All right, given the rambunctiousness in the classroom, I'm sure you got all into your discussion about sample sizes, about what it is that you enjoyed. All right, so now I can actually type in Excel. I can show you what I want. So we've got these sample sizes that we established earlier. I'm just going to go ahead and plug these back down in our table here. Hope so. Works out. All right, so let's just go ahead and look. We've got some testing that occurred in our tests, okay, or some results from our tests. So it says number of deviations. For a sample size of 4, or sample size of 127 is 4. So my sample deviation rate is just 4 divided by 127, which is going to be 3.1%. Okay. I can do that for all of them, which I'm going to do to save time. I can just divide 2 divided by 88, 2 divided by 96, and 0 divided by 76. Now, what we can use is we can use that second set of tables to determine, based on the number of deviations on our sample size, what is our computed upper deviation rate. And part of the reason that I want to use IDEA today is because what we're going to find is that this is not particularly effective because some of our numbers don't really have good round results. So I'm going to say I found 4 deviation rate. This is for confidence level 95%, which is our third table. I found 4 deviations in a sample of 127, sample of 127, which 125 is about as close as we can get. So we're going to say 7.2. If you remember, our tolerable deviation rate is 6%. So we can tolerate a 6% difference, but we're projecting the highest possible difference we can see in the population is 7.2%. What does that mean? It basically means that we cannot accept this control as effective because of that result. We're saying that the possibility of a population deviation rate of 7% is greater than the 6% tolerance that we have up here. So our conclusion is going to be not effective. And again, we can plug those in. Let's just go ahead and do number 3 again, just for context. So we have a number of deviations of 2, and this is going to be on our table for 90%. So if we go over here, 90% confidence level, 2 deviations, and the sample size, which I should have picked up 4, was 96. Which generally we start at the one that's lower. We start at the lower end. Even though 96 is closer to 100, we're going to be conservative and go to 5.9%. So 5.9% and a tolerable deviation rate of 4%, that's going to be not effective as well. Now, the problem is that, just as a spoiler for what we're going to talk about here in just a second, one of the big problems is that when we use tables, we have imprecise measurements. Okay? This is fairly apparent when we start talking about something like 0 deviation. So you performed a test of 76 items. All 76 items came back effective. But because we have a really, really small tolerable deviation rate, we still ended up with a computed upper deviation rate of 3.3%, which is really unsatisfying. You basically did test work for nothing. So this is part of the reason I want to talk about IDEA today. One of the reasons for this, first of all, tolerable deviation rate of 3% is ridiculous, okay? But another reason I want to talk about it is there's a lack of precision when we use numbers like 88 or 76 because those are not round numbers, and using tables creates problems for those. So what I'm going to do is I'm going to show you why we can use IDEA as a sampling tool, and this is why one of the big benefits of it. So one of the reasons I like IDEA and why I'm sad that we can't do it this semester, but I do think that there are some real benefits for that. Before we do, though, we need to talk about a few more things. We need to wrap up with talking about variable sampling. So I don't really go too much in detail as far as variable sampling. You won't have to do too much extrapolation. We're going to run through a quick exercise here in just a second. But basically, this shares a lot of the common traits with attribute sampling. Again, the big difference is that we're looking for a number rather than the existence of a deviation. So instead of saying tolerable deviation rate, we're going to be dealing with tolerable misstatement. And you guys have heard that term before. Tolerable misstatement is what we establish as the maximum misstatement that can exist in the counter disclosure. So tolerable misstatement is basically going to be inversely related to sample size. So the larger that tolerable misstatement is, the smaller our sample we need to test. So we'd rather have a large tolerable misstatement than a small dollar one. Gives us a little bit more room. And then we have our projected misstatement, which is the estimated misstatement in the counter population or counter disclosure. We're going to be using something called the upper error limit, which is kind of the analog to that upper deviation rate. What we compute to be the projected misstatement after we see what the sample misstatement is from our testing. So if our projected misstatement is less than our tolerable misstatement, we conclude the counter disclosure is fairly stated. If our projected misstatement is greater than the tolerable misstatement, then we say it's not. So basically, if our tolerable misstatement is larger, we're saying everything's fine. What we project the misstatement to be in the population is less than what we can tolerate. But if this number is greater, then we're saying this is greater than what we can tolerate. So that's basically how we interpret that. Very similar interpretation to how we look at attribute sampling. It does involve a little bit more critical detail and a lot more statistical analysis than I'm comfortable with doing in this particular course. So we're going to keep it fairly simple. That being said, like I mentioned earlier, a lot of times when we do techniques like this, we will have tools at our disposal, either methods that are established by a firm or statistical analysis tools that we can use to make this a much simpler task. All right, so that does it for the lecture part, but I do want to run you guys through some IDEA activities to show you how we can use IDEA to improve some of the work that we do. So the very first thing is I want to talk through some problems that you were going to be given an IDEA. And if you've got access to them, you can look at them to see the problems. Otherwise, you can just walk along with me. So in the problems, basically, we're going to be talking about how we actually set up sampling. And let's just go ahead and we're going to use the IDEA tools. You don't actually need to have a file open. That was one of the drawbacks before, because we're just doing some speculation testing. We're not actually testing a specific file. So if you don't have these files here, which I assume you don't, because these are actually Chapter 5 assignment files, So you're going to look a little bit different than what you have on your idea or what you have idea program open. What we're going to be doing though is you're just going to be doing some basic analysis. So if you go to analysis, then you notice a few are still available even though we don't have a file open. So let's go ahead and click on attribute. And again, you're not required to do this. This is not required if you want to look on somebody else's computer. If you just want to watch me, whatever you want to do is fine. This is not something I'm testing on the exam. This is just for clarification of how we can use statistical tools for help in this area. So let's go ahead and just enter some basic information. What I'd like to do is I'd like to enter a population size of 1,000. I want to do a deviation rate of 3, tolerable deviation rate of 8, and a confidence level of 95. So just for context, what this means for our sample testing is that we're specifying a population, which is a pretty small population, and it can vary. We're going to make this much larger in a little bit so we don't have so much variance. But we're looking at a confidence level of 95%, saying that we can tolerate 8% difference in the population, and our expected difference is going to be 3%. So there's a difference of 5% here, and 95%. So let's just go ahead and compute and see what sample size we need to test in order to get assurance here. And you will notice that the sample size is 91. This is telling us that based on these factors that we speculate here, we would need to test 91 items to have a sufficient sample for testing to get this level of assurance. Now, this is all well and good. This is much easier than using a table. But let's just go ahead and see what happens based on what we already know, what we talked about when we change some of this information. So I'm going to change details here, and you can, again, do these with me to see what happens. But the important point here is not seeing how to change, but speculating on what will happen when we make these changes. So the first change I'm going to do is I'm going to change my confidence level to 90. All right. Based on what we know about confidence level, do you predict my sample size will go up, down, or not change at all? I predict my sample size will get smaller because as the confidence level gets smaller, my sample size should get smaller. I need less assurance. So we'll notice it dropped down to 63. Okay. So now let's go back to 95 and let's make another change. I'm going to increase my population to 500,000. So what's probably going to happen to my sample here? It's going to go up, but it's probably not going to be as much as you think. It's increased by 500 times. I don't think my sample is going to go up by 500 times. Okay. So remember, my original sample was 91. I think it will increase 95 now. So I increased 4 items in the sample by increasing my population by 500 times. So that's kind of an explanation that sample or the population size does not have a big effect. All right. I'm going to go ahead and change this back to 1,000. So we're back at the default. So should we go back to 91? What about expected deviation rate? I'm going to change this to 4%. Not 40%, just 4%. What do you guys think? What's going to happen now? The sample is going to get larger or smaller? I think my sample will get larger. Okay, my sample will get larger. There we go, 123. Why is that the case? Again, remember the distance between this number here, the tolerable deviation rate, and expected deviation rate, dictates how large the sample is. If this is a smaller distance, then the sample gets larger. If it's a larger distance, the sample gets smaller. Okay. Let's go ahead. Put this back at 3%, so we go back to our default. Oops. Back at default to 91. Now I'm going to change this to 7%. What do we predict now is going to happen? Sample size get larger or smaller? Be larger, okay? There we go, 123. Again, the distance got smaller here, so that's why our sample got larger. What happens if I change this to 15%, though? So instead of, why is this not working? Numeric? I think I hit numeric lock accidentally. Okay. I change this to 15%. What's going to happen to my sample size now? Get much smaller. Yeah, much smaller. Because there's a big distance between these two. Here's an interesting question. Let's just kind of speculate on something. What happens if I set this to my default at 8%? Because remember, I started at 8%. And I'm going to set expected deviation rate to 7.99%. Okay. What's going to happen to my sample? Obviously, it's going to get, my sample's going to get larger. Okay, it's much, much larger. What do you guys guess? What's your guess for the number of sample size out of 1,000? I'm going to guess 1,000. Okay. How about that? So what is happening here? Okay. I'm basically saying that what I expect to be see in the sample, the deviation rate I expect to see in the sample, is so large, so close to that tolerable deviation rate that I have to test everything to be sure. Okay. So the smaller this distance gets, this increases pretty substantially. If you get close enough, basically it says you got to test everything, bro. Okay. Basically what's going to tell me. Now, which of these factors do you think had the biggest effects? Okay. I think probably confidence level had a pretty big effect. Okay. Confidence level changes. And then our rates here, our rate changes had a big effect. Population size, probably not so much. Probably not so much. All right. So let's go ahead and let's click on the next tab over here. It's called sample evaluation. We're gonna ignore planning. We're not gonna do that. But this is going to tell us what the results of our sample testing are. So instead of saying what our sample size, not got our sample size, now we're going to actually look at some results. So let's say that we have 3 tested controls, okay, and we did a sample of 52 items for each of these tests, but they had different number of deviations. So let's go ahead and set a population size of 1,000. Come on. We're going to say sample size of 52, and we'll say confidence level of 90. All right. Now I'm going to say my first test, I had 2 deviations in the sample. So I need to determine what's going to happen here. Is this effective or not? Anyone have any guesses on this? You can actually just click compute and answer this, I guess, on your own. So this is basically telling us that for an observation of 2 deviations in the sample size, I can be sure that the population deviation rate is no more than 9.7%, okay? So it's important for us to be able to note that if I'm going to answer this question, I need to know what. If I'm going to answer this control is effective, I need to know what. I need to know, first of all, my tolerable deviation rate, okay, which I didn't specify. In the previous question, it was 8%, but let's just go ahead and assume it's 7.5% here. So the tolerable population deviation rate is 9.7%. My tolerable deviation rate is 7.5%. Is the control effective? 50% chance, guys. Don't want to be wrong. Yeah, I'll give you a 100% chance. The answer is no. Okay. The answer is no. All right. Why is it not effective? Well, basically, what we're saying is that in our sample here, it's roughly a 4% deviation rate in the sample. But we added an allowance to sampling risk to it. We added an arbitrary allowance basically to increase the range. And we said, we think that the population could be as high as 9.7% deviations based on 2. Because we used a very small sample, so it's going to extrapolate pretty heavily. So based on 2 items, we believe that the sample, the population deviation rate could be as much as 9.7%. What can we tolerate as far as deviation rate? We can tolerate as much as 7.5%. So if we can only tolerate 7.5%, but our expected population deviation rate can be as high as 9.7%, that's too much. It's too high. Therefore, we have to reject this. So let's go ahead and keep our staging factors, but let's change the deviations in the sample to 1. What do we got now? It says the deviation rate is no more than 7.1%, 7.1. So population deviation rate is 7.1, tolerable rate is 7.5. Control effective. Control is effective. The tolerable deviation rate is higher than expected population deviation rate. Okay. And our third example is just saying it's 0. Okay. So if it's 0, obviously the population deviation rate is going to be 0, right? Nope, that's not the right answer. So why am I saying that? Okay. It's important to keep in mind that even if we observe 0 deviations in the sample, that we have to add something onto the expected, or to get the expected population deviation rate. Because out of 52 items, we notice 0 deviations. Does that mean that there are 0 deviations out of all 1,000 items? No, it means that we expect that there's probably between 0 and some percentage. And IDEA is telling us that the highest we probably could likely see, most likely scenario, is 4.2. So between 4.2 and 0 is probably the range that we're looking at. So as long as we're above 4.2 as far as tolerable deviation rate goes, we're fine. Because this is the maximum we can see in the population. Now, this would make me really, really angry if I was doing testing and my tolerable deviation rate was like 3, and I'm looking and saying, I tested the entire sample and nothing came up, and I still have to reject. Okay, that would make me very, very unhappy. But let's go ahead and let's look at some scenarios like that, because you will notice that we can actually plug in our numbers that we did in our earlier testing to come up with a little bit more satisfying conclusions. So let's go ahead and set this population size at 500,000. All right. And then remember, when we were looking at this before, we looked at a couple scenarios in problem number 828, I think it was what it was. 828, and yeah, I'm going to go ahead and move over here. So 828, and we had a sample size in our first scenario of 127, and we had a number of deviations of 4, okay? And we compared this, we did the analysis. What was our conclusion here? Did we conclude that this was effective or not effective in our first scenario? We were doing this by table. We concluded it was not effective, okay? So does this match up to what we said? That sure makes sense, okay? Because remember our example, our tolerable deviation rate was 6%. This is saying that the population deviation rate, the expected population deviation rate is 7.06%. So that's still consistent, which makes sense because 127 is the number we were using, but on the table it was 125, which was really close. Now let's look at a few other numbers. Let's look at the numbers that we didn't take a look at. Let's just examine those, okay? So we're going to leave population size at 127. We're going to change our sample size to 88. We're going to change our number of deviations to 2, and we're going to leave our desired confidence level at 95. We're going to compute. And this one's interesting because this was our second scenario. We didn't actually calculate the second scenario, but in our second scenario, if you do this by table, you come up with the conclusion that the control is not effective because our tolerable deviation rate is 7, and using the table, we come up with an upper error limit that's greater than 7%. But if I use IDEA, which can actually calculate specifically at 88, that specific number, you will notice that our upper error limit is 6.98. Now, 7% is greater than 6.98, just barely, but it's still greater. This would be where I was an auditor, I would pump my fist and said close, but it's still below. So I can accept this test as being effective. Again, this is why having a tool like this is so much more powerful because it gives us a much more precise estimate. And just for closure, guys, just for closure, let's go ahead and do one more thing. We have to do this because otherwise it's wholly unsatisfying. Change sample size to 76. Oops, not 43, 76. Change number of deviations of sample to 0, and we're going to change our desired confidence level to 90. This was actually the fourth scenario, which remember I said that we had to conclude it was not effective. But if we do it in this scenario, 2.98% was our expected population deviation rate. Our tolerable deviation rate was 3%. So we conclude that control is effective, all right? Which makes all your hard work pay off. So you can give yourself a round of applause or a pat on the back, whichever you prefer, okay? All right. So let's go ahead. I'm going to show you one more thing. You probably won't be able to work along with me here, but I do want to do one more thing to show you some powerful tools here. So that was attribute sampling, and you can actually work attribute sampling on your own. And again, if you run into a situation that you actually come into that scenario where you've got to do attribute sampling for a statistical assignment, you can actually use IDEA to help you on this. But now I want to do an example of how we would use this for monitor unit sampling. So I'm going to open this table. Basically, well, I'm going to open two tables. So I'm going to open this first one, the accounts receivable table and accounts our monetary sample, which again, in past classes, you would have this table, but because IDEA is not working, none of you have this table. So I apologize. That's just the way technology goes sometimes. But what do I want to do here? What are some analysis that I want to perform here? So let's just go ahead and see what kind of monetary analysis I can perform. So I'm going to say, let's go ahead and we're going to create a sampling plan. So monetary unit plan. And I want to test the invoice total. And I'm going to set confidence level at 75%. Now, what is this saying, confidence level at 75%, by the way? Means that I have 75% confidence the numbers that my results are accurate. How confident would you be if you were a client working with an auditor and they said, I'm 75% confident? Not very. This is not a number that you would use in real sampling, by the way. I want to clarify this. If you see me 75%, it says, oh, we can go that low? No, you can't, okay? This is just for illustrative purposes, all right? Just for illustrative purposes. Tolerable error, we're going to set at 30,000. And expected error, we're going to set at 1,000. And I believe that's all we're going to say. So we're going to say estimate. And basically what this is telling me is that it's saying that if I want 75% confidence, I have to test 28 items out of this population, which this population is 454 records, okay? Which it already knows that because it's actually got the table in front of me. So that would be good from a work perspective. Be like, wow, 28, that's easy, okay? But my boss is probably saying, why did you use 75%, you nitwit, okay? And I'd deserve to be called a nitwit in that situation because 90 is about as low as we can go. But the reason that we do this is so we can actually use a smaller sample. Now, interestingly enough, this is kind of the instructions that IDEA gives, and they want to kind of keep the sample really, really small. But assuming that I want to achieve 75% like that, I've got a very low standard. Basically, I'm fine with 1 out of every 4 records being completely misstated, okay? I don't know if that would be something I'd be comfortable with in auditing, but 1 out of every 4 records being misstated, I'm fine with. All right. I can actually use this to perform some testing. So basically, IDEA will allow me to create a random sample here, which is what I've done. And again, since we're not testing on this, I'm not going to tell you exactly what happens. But we can also use to create virtual fields. So you'll notice here's the invoice total, and I created a new field called audit amount, which allows me to test and say, all right, what was my exact result? And I changed the first 2 items. You'll notice this is 244 and 112.57, and I put an audit amount. This is supposed to replicate if I tested and I said, this number is actually only 44.24. This number is actually only 1157.59. So I have differences in my sample. How do those differences extrapolate to my population expectations? Well, first of all, it's going to be enormous. And the reason why is I've only tested 18 items. That was my sample size. Is 18 items a sufficient sample size for what I'm trying to test? Not even close. Remember, for 75% confidence, I had to have 28 items. I tested less than or fewer than 28 items, which means that I'm not going to be very confident at all, okay? I'm not going to get anywhere close. Let's just go ahead and look and see what happens. I'm going to go to monetary unit. I'm going to evaluate and sell in classical PPS. And it kind of has my numbers already put in here. My confidence level 75 that I already specified a sample size of 18. And I'm just going to go ahead and leave that those number correct because I've already got those plugged in from previous attempts. Click OK. And it's going to give me some results that are going to be very unpleasant, assuming that it can finish the task before class ends. This is not something I expected. I thought, okay, we've got through the worst part of it. I didn't think that we'd actually get stuck here. So hopefully it will come up. Yep, it looks like it's getting there. Okay, so hopefully it'll come up. This table is a lot of gobbledygook, but it's basically saying that the possibility is that my population, or the population for $300 in differences in my sample, because remember, I had one item that was misstated by $200, and I had another item that was misstated by $100. The population misstatement could be as high as $70,000, which is kind of ridiculous. So why is that misstatement so large? Part of it is because we use so few in our sample. So whenever we use so few in our sample, any errors we see get magnified by a greater amount. All right. That being said, could we accept this? If I brought this to my boss and say, okay, here's what was the results of my testing, he would say, well, you were supposed to test 28 items for your ridiculous confidence level, but you only tested 18. And this is telling us that we can have a misstatement as large as 70,000. Does anybody remember when I was working this earlier, when I said my tolerable or my highest level of misstatement was? It's 30,000. This is much greater than 30,000. So I would not be able to accept the results of this test. I'd say substantive testing for me. That's the way that I'm going to be going. Much more detailed testing. Or in all likelihood, my boss would say, yeah, redo the test with a realistic sample and a realistic confidence level. But this is kind of an example of how this can help out in something like that and make a task a little bit easier, even though it's not necessarily a satisfying conclusion. All right, we have homework on Friday. I will see you all then.